Hi everyone, Mr. Boltri here bringing you video 6.5. We're going to be talking about friction and drag. Now, one thing I want to say before we get started is for some reason when I was making this video, I put a lot of words on the slides. So the good news is that hopefully I'm not going to go off on very many tangents, but the bad news is there's a lot of words. So make sure you're not writing down every single word or your hands are going to start to hurt. So just write down the most important ideas from all the different slides. So let's get started. Let's talk about friction. Friction is a force caused by the rubbing together of two surfaces. We talked about the direction of friction is always in the opposite direction of motion. So if an object is moving, friction tries to get the object to slow down and stop by working in the opposite direction of the motion. And for a stationary object, friction acts in the direction against the object's desired motion. And I define desired motion as if friction were to disappear, what direction would the object move? And friction acts in the opposite direction of that. So we talked about the difference between static and kinetic friction. Static friction is when an object is stationary, and friction is trying to stop the object from moving. And kinetic friction has to do when the object is already moving, and friction is trying to get the object to slow down and come back to a stop. So in our lab, we were measuring static friction because we recorded the amount of force it took to get an object that was stationary just to barely move. Specifically, we were actually measuring the maximum amount of static friction. So static friction could be any number less than the maximum amount, like it could be 1 Newton, 2 Newtons, 3 Newtons, all the way up to looks like 5 Newtons. And once you push or pull for more than 5 Newtons, then you're going to overcome that static friction and then cause the object to start to move, which then gets in the kinetic friction territory. So the tricky thing about static friction is that it can also be less than the maximum amount too. So if the maximum amount is 5 Newtons, the static friction could be like 3 Newtons or 2 Newtons. So for example, if in the diagram on the left, if I pushed with 4 Newtons of force, static friction would rise to match that applied force. So if I pushed with 3 Newtons, the static friction would also be 3 Newtons, because the balanced forces would equal constant velocity. And so if the forces were balanced, then the object wouldn't move. So 3 Newtons to the right by my push, 3 Newtons to the left by friction, balanced forces, constant velocity of 0. And then if I push more and more, I can push all the way up to the breaking point, and then I can push past the breaking point, and then the object starts to move because unbalanced forces equals changing velocity. So static friction increases to match the amount of applied force until it can't anymore. It can't anymore when you go past the force friction maximum. So when the static friction can no longer increase anymore, that's when the object begins to move. That's why it's called the breakaway point. The object breaks through the static friction and then begins to move because the forces are now unbalanced. So when we use the formula for static friction, it only tells us this maximum value. But we have to remember that it can also be less than that maximum value as well. So unlike static friction, kinetic friction acts constantly when an object is in motion until the object that has slowed down to a stop. So you'll see here, the kinetic friction is pretty constant. It wavers just a little bit, but the kinetic friction acts constantly, and we don't have to worry about, as long as the object is moving, we can determine the amount of friction acting by just using the formula, the kinetic friction formula. We don't have to have information about what the applied forces acting in the object are. So with that in mind, let's talk about our lab results. In our lab, we found the relationship between force normal and force friction to be linear. What that means is as force normal increases, force friction increases also. This makes sense because force friction is caused by the rubbing together of two surfaces. So if two surfaces are smushed together extra hard, which would be high force normal, that means there's going to be a lot of force friction. We also found that the different groups had different slopes. As we determined as a class, these different slopes were because different groups used different surfaces. The groups that had the smoother surfaces, like the red team, had a shallow slope. And the groups that had the rougher surfaces, like the green team, had a very steep slope. So using our linear relationship, we concluded that force friction equals the slope times force normal. And we said the slope basically determined how rough or smooth the surface was, with the rougher surfaces having the steeper slope and the smoother surfaces having a more shallow slope. So we actually determined that the slope has a fancy scientific name, which is called the coefficient of friction. And it's represented by the Greek letter mu, which looks like a kind of a M and a U. So the coefficient of friction is a unitless, because it was newtons divided by newtons, number that serves to quantify, like a multiplier, how much roughness there is in a surface. So if a surface is very rough, for the same amount of force normal, we're going to have a lot more force friction because we're multiplying by a bigger number. We are multiplying that force normal by a bigger slope. So after all that, we got our friction equation, which is force friction equals mu, the coefficient of friction, times the force normal. And here you can see that if I have a higher mu, a higher coefficient of friction, and I multiply by the force normal, that's going to give me a bigger number for my, a bigger coefficient of friction times the force normal is going to give me a bigger force friction. That's why I call it the force friction multiplier, because I multiply it by the force normal. You multiply force normal by a big number, you get a big force friction. You multiply force normal by a small number, you get a small force friction. The one thing that we didn't really talk about in class that I really want to clarify is that this formula tells me the magnitude of force friction, and then we have to know, we have to think about which direction it's going to be. The reason why it can't give me the direction is because force normal is up. So force friction is going to be in a different direction, usually horizontal, either left or right. So it'd be more accurate to write it like this with the absolute value bars, to show that this formula tells me the absolute value, the magnitude of the force friction, and then we have to think about what direction the force friction is in. Also, since there are two types of force friction, we have to know the two different equations for force friction. One of them is for static friction, which uses the coefficient of static friction, and one of them is for kinetic friction, which uses the coefficient of kinetic friction. Just as a note, the coefficient of kinetic friction is almost always less than the coefficient of static friction, because it's easier for an object to keep moving once it's already moving than to get past that breaking point where it's kind of stuck. And you'll notice also a little reminder about the equation for static friction is that when we're calculating static friction, this formula gives us the maximum amount of static friction. So the actual amount of static friction in a given example may be less than the maximum amount, but it can never be more than this maximum amount. So now let's talk about drag force. Drag force is also called air resistance. It's like the friction in the air. However, it applies to a liquid or a gas, not just the air. So it could be going through water or air or whatever sort of liquid or gas you might be moving through. The fluid that you're moving through, whether it's water or air or whatever, we call that the medium. That's just the fancy science name for the liquid or gas that you're moving through. Like friction, drag acts in the opposite direction of motion, but unlike friction, drag is caused by actually bumping into the molecules of the medium. So for example, air. When we bump into the air molecules, it causes a force that pushes back on us and slows us down. So what are the factors that increase drag? If you think about times where you've experienced a lot of drag, what were the factors that increase the drag? So there's actually 5 that we need to know. One is a big surface area. And that's why parachutes, skydivers open the parachutes, because then you hit more air molecules. If you're moving really fast, then you're going to hit a lot of air molecules. Or if the air is moving really fast, then you're also going to hit a lot of air molecules. If the medium is really thick, for example, water versus air or honey versus water, then you're going to hit more air molecules or hit more molecules of the fluid just by going through it based on how thick it is. And the last thing that's going to influence it is the object shape and also the texture a little bit. So these are the 5 things that influence drag. And the most important question to remember is what is going to cause you to hit more air molecules? If it causes you to hit more molecules, it's going to cause more drag. More molecules, more drag. So the equation for drag is force drag equals 1/2 times the thickness of the medium times the relative velocity of the medium and the object, sort of either the medium is moving fast or the object is moving fast, the surface area, and the drag coefficient, which is mostly affected by, you guessed it, the object's shape. So the important thing that you need to know about this equation is you do not need to memorize it. You do not even need to know it to use it on a quiz. You can write it in your lab notebook, but the most important thing that you need to know is the 4 factors that affect how much drag there is, or actually really the 5 factors. One is the density, like we talked about with the honey. One is the relative velocity, like when the plane was going fast or when the wind was going fast. One is the surface area, like with the parachuter, and one is the shape, which is how we get the drag coefficient. So I wanted to show you both in picture form and in equation form how we can remember those 5 factors that influence drag. But those 5 factors can all be summed up by one idea, and that one idea is the more air molecules you hit, the more drag there's going to be. The last thing I want to talk about is some people, when they see this equation, they like freak out. They're like, oh my gosh, there's a squared in there. There's a 1/2 in there. There's so many variables. And what I want you to understand is that the people who develop this equation use the exact same methods that we've been using in class to develop equations. So you could, if you wanted to, go to a aerospace engineering lab and then do enough experiments to get this equation. Like, you have the capability of deriving something that's complicated and scary like this. Now, whether you want to or not is a different question, but the most important thing I want you to take away from my class is the ability and knowledge that you can figure out really hard things like the drag equation or whatever difficult things that you want to figure out. So on that, this is Mr. Boltri wrapping up video 6.5 on friction and drag. Looking forward to answering your questions next class, and also doing a lot of practice problems before we take the quiz. But for now, go Bears.